Hello, Benedict here from www.preciseload.com, the internet's most accurate interior ballistic calculator. In the previous episode of Firearms pressure and velocity factors, I explained the basics of the gas pressure curve. In this episode, I want to discuss the influence of propellant mass and type on gas pressure and muzzle velocity. For this, I will share gas pressure measurements that I conducted for the development of www.preciseload.com at the Melristadt Proof House. Point 3 will be particularly interesting for many listeners. Here, I will also demonstrate through measurements the negative effects of low charge densities. For the experiments, I used new Lapua brass in 308 Winchester, paired with 168 grain Sierra hollow point bowtail MatchKing bullets. Both brass and bullets were from the same batch. Various types of reload Swiss and Vihtavuori propellants were used. For all experiments, as explained in the first video, great emphasis was placed on a verifiable experimental setup. In this first series of experiments, I only increased the powder mass in steps of 2 grains for various powders. The case, the bullet, and the seating depth remained unchanged. In the left diagram, the development of gas pressure over time for various powder masses of the RS50 type is shown. It's noticeable that peak gas pressure increases with increasing powder mass. Particularly interesting is how precisely this increase occurs. For this reason, in the right diagram, I've only shown the peak gas pressure as a function of the powder mass. It is clear that the gas pressure doesn't increase linearly, but exponentially with the powder mass. Let us compare the gas pressure increase when the powder mass is increased from 36 to 38 and from 44 to 46 grains, marked here by the green and red dotted lines. Although only 2 grains of additional powder were added in each case, the gas pressure increase in the first case is not even 200 bar. However, from 44 to 46 grains of powder mass, the gas pressure increases from around 3,600 to 4,200 bar. In this case, the additional 2 grains increase the gas pressure by 600 bar. Even if other powders, bullets, and cases do not show an identical curve, this exponential behavior is typical for all propellants. Now, I want to address an important point that can lead to inaccurate and dangerous loads. We once again consider the blue dashed regression curves in the right diagram. It's wrong to assume that loads with very little powder are always safe. Unfortunately, due to so-called secondary explosions, this is not the case. More on this on the next slide. In this experiment, gas pressures were also measured at low charge densities. We observe that with loads with low powder density, that is below 75%, peak gas pressure and thus muzzle velocity fluctuates significantly more. At low charge densities, there are often secondary explosions with peak gas pressures far exceeding the tolerances of firearms. It is suspected that these secondary explosions are caused by uneven ignition. In addition to the danger of overpressure, loads with charge densities below 75% are therefore often very imprecise due to the resulting scatter in gas pressure. After discussing the influence of powder mass, I will now address the next important aspect, the vivacity of the propellants. This term refers to the speed at which a propellant burns and releases energy. Fundamentally, propellants can be divided into slow and fast-burning powders. In early German literatures, the terms lazy for slow powders and lively for fast powders were often used. For rough orientation, most powder manufacturers provide comparison tables that indicate the vivacity of their powders compared to other commercially available powders. However, these tables are only partially suitable for load development, as I would like to demonstrate through a series of experiments with the RS50 and N150 powders. According to the corresponding tables from Reload Swiss and Vihtavuori, these powders have a fairly similar vivacity. Although according to the tables, N150 is slightly faster. Now let's look at the results from an experiment in which I measured identical loads for the slow RS50 and the fast N150 powders at various powder masses. First, we look at the left diagram. It shows the gas pressure curve for both powders at identical powder masses. We see that the faster N150 powder leads to higher gas pressure and burns overall faster. This is not surprising and to be expected. Now let's look at the right diagram. This shows the peak gas pressures for both types of powder at different powder masses. It becomes clear that from about 45 grains, the nominally slower RS-50 powder seems to surpass the faster N150. This small example illustrates that vivacity alone is not sufficient to understand the complex interaction between powder, charge mass, and other variables. The final slide will focus on the relationship between gas pressure and muzzle velocity. As immediately apparent from the left diagram, peak gas pressure strongly correlates with muzzle velocity. However, in this case, the relationship is not linear. We see that muzzle velocity increases only slightly with increasing peak gas pressures. Muzzle velocity increases only relatively little after perhaps 3500 bar. Attentive listeners may rightly conclude from this that with NC powders, a certain maximum bullet velocity cannot be exceeded. Finally, let's look at the right diagram. It shows muzzle velocity as a function of powder mass. At least approximately and with typical charge densities, this relationship is linear. Unfortunately, this relationship doesn't help us for the development of a safe load. From this video, it can be inferred that interior ballistic calculations aren't simple. However, with precise load, the most precise interior ballistic calculator on the internet, the calculation of gas pressure curves and muzzle velocities is in the end quite easy. So, subscribe to my channel and feel free to try out the beta version of www.preciseload.com. I've already added the real names for some powders. Oh, by the way, in the next videos, I will explain the influence of bullet type, mass, and seating depth. Again, there are interesting measurement results available. Following this, there will be a video describing the application of precise load and the achieved simulation accuracy.